All right, well, I'm going to go ahead and get started here, going over the study guide. Remember that the test is on Tuesday at 1 o'clock, like our last test was. During this time, we have covered work, energy, simple machines, and then a little bit of electricity and magnetism. So I'm going to start out here with talking about energy, potential energy, and kinetic energy as it is shown in a pendulum. So a pendulum is basically, it's just a mass that's on a string and it swings back and forth, kind of like a swing set or inside a clock. You can see a pendulum swing back and forth. But basically, it goes up to its maximum height and its minimum or smallest velocity. In fact, when it gets up to this point right here, the velocity is 0. All right. Then it starts to swing down. It gains speed until it gets down to the bottom here. And down here, we're at our minimum or smallest height. And we are at our maximum velocity. All right. And then it continues to swing until it gets back up to this place where, again, it has its maximum height and its minimum velocity, which is, again, 0. Okay, so this position and this position are the same. All right, and this position is different. This is the lowest point. So the first question says, where does a pendulum have the most potential energy? Well, it's going to have the most potential energy when the height is the greatest. Okay, so this is where you're going to have the maximum height, which means you're also going to have the maximum potential energy, the most that you can have. Okay, and the same is going to be true over here. So then it says, number 2, where does a pendulum have the least potential energy? Well, it's going to have the least potential energy where the height is the least. Okay, and that's at the bottom. So down here, because it has the minimum height, that means it's also going to have the minimum potential energy right there at the bottom. Okay, in fact, we could say that this position has 0 height. We could choose that this is where 0 is on the height scale. All right, number 3, where does a pendulum have the most kinetic energy? Well, it's going to have the most kinetic energy when going the fastest. All right, and where is it going the fastest? This place right here where the maximum velocity takes place. So, hi, Claire. Oops. So you're going to have where you have your maximum velocity, that's where the kinetic energy will also be the greatest at the bottom. And if you've ever been on a swing set, you know that you're going the fastest here, and then you start slowing down again. So then where does it have the least amount of kinetic energy? That's going to be at the places where the velocity is 0. So when it's slowest, all right, and that is at the top. And we already talked about, you know, where does it move the slowest? Where does it move the fastest? It moves the slowest at the bottom, or I'm sorry, at the tops. And it moves the fastest at the bottom. If you have a question, feel free to just type in a chat thing, and then I can answer that. If you want me to slow down or go over something again, I can definitely do that. All right. What is the so that covers the pendulum. So we're going to move on from the pendulum. And now we're going to get into some other definitions. Number 7, what is the input force? All right, so now we're asking questions about machines. And remember, a machine is a simple machine is a device where you can change the force or direction of the movement of an object with just one motion. So for example, if I have a teeter-totter, okay, that's a simple machine. All right, now, if I want to use this teeter-totter to lift up this box, if I want the box to go up, I have to push down. Okay, this is the force in, and this is going to be the force out. The force in comes usually from a person. It doesn't have to, though, but we'll just say, we'll just call that force input my force. And the output force is the force the machine exerts. Okay, what is the work output? The work output is the work the machine does. And the work input is the work that I do, or the work that a person does. And it doesn't always have to be another person. It could be a truck, or it could be another machine actually doing work on a simple machine. Now, one thing I would like to point out is that work output is always less than work input on a machine. Always. There are very few things in life that are always or never true. This is one of those few things. Work output is always less than the work input. All right, number 11. What is a screw? How is it related to an inclined plane? A screw is a simple machine. It's basically, I think you've probably seen a screw before. You know, it looks something like this. And you use it to attach, you know, things together. Basically, the question is, how is it related to an inclined plane? And basically what a screw is it is an inclined plane that's wrapped around a nail. All right. And again, you're not going to have to really know exactly how to explain it that way, but just know that a screw and an inclined plane are both sort of forms of the same thing. Sorry, got kind of a mess here. All right, number 12. What is a first-class lever and what kind of mechanical advantage does it have? All right, or advantages. A first-class lever is one where you have your input force and your output force on opposite sides of the balance point known as the fulcrum. Okay, they're on opposite sides. And the mechanical, you can have any kind of mechanical advantage here that you want. So the mechanical advantage can be greater than 1. It can be exactly equal to 1, or it can be less than 1. So what does it mean to have a mechanical advantage greater than 1? It means that if you push down with a little bit of force, it will lift with a great amount of force. Okay, that's a really good thing. If you have a mechanical advantage of exactly 1, that means that however hard you push down, that's how hard it will push up. The forces are the same. And if you have a mechanical advantage of less than 1, it means that you have to actually push harder than the machine does, which you might think that's kind of, why would anybody want that? And the reason is that it gives you more distance. It will move a greater distance. I would recommend checking out that video that went along with the mechanical advantage of, or that, I'm sorry, the lever video. That would have been back in the lever or the simple machines category on Classroom. Now, mechanical advantage of 1, again, you might be saying, well, why would I want to use that? It's not going to do anything. It's not going to increase my force at all. But look at this here. If I push down, I can sit on this. I don't have to use my muscles actually to lift this object up. I can use gravity and my own body weight to push that up. All right, a second class lever now, we take these 3 things, the force in, the force out, and the fulcrum, and we rearrange to get this. All right, so now I've got my fulcrum on one end. My output force goes in the middle, and my input force goes on the outside. So the output and the fulcrum switch spots from the first class lever. Now, in this case, you always have a mechanical advantage greater than 1. All right, this always makes it easier to lift things. And examples of this would be like a wheelbarrow, where you have a big pile of dirt and you lift up at one end and there's a wheel at the other end, something like this. Okay. Here's the output force. Here's the input force. And this is the fulcrum, the wheel of the wheelbarrow. But it's easier to lift. It could weigh, 200 pounds, but you don't have to lift with 200 pounds. You might have to lift with 50 pounds to lift it up, which is a pretty sweet deal. All right, third class lever. Again, we have the fulcrum at one end. But now we lift in the middle, that's the input force, and our load is on the outside of it. Now, again, this is going to make me lift. If I set something up like this, let's say this was 50 pounds, I might have to lift with 100 pounds here. My mechanical advantage is going to be less than 1. But if I only lift up 1 foot here, let's say I lift up to this position, okay, it traveled this whole distance, even though I only had to lift that much. All the muscles in your body are set up as third class levers. So when you do an arm curl, or you're lifting weights or something like that, you pick something up in your hand that might weigh 10 pounds, your muscles are actually probably exerting well over 40 pounds of force to lift that up. But they only have to squeeze little bits and move a little bit to make it move a long way. So 15, give an example of each kind of lever. First class lever right here, this would be like a teeter-totter. Hopefully you can see that. I already gave you an example for a second class lever. That would be a wheelbarrow. And this would be like the muscles in your body, or say a fishing rod as a third class lever. Okay, number 16, what is power? Power is the rate of doing work. Okay, so it's actually how fast you can get work done. If you're being really powerful, you're getting a lot of work done in a very short amount of time. If you're not being very powerful, you're just kind of taking your time and getting the job done. The example I would give here is going up the stairs. It takes just as much work for me to walk up the stairs as it does to run up the stairs. However, I need to be more powerful to run up the stairs. All right, number 17, what is mechanical advantage? Mechanical advantage is how much a machine multiplies your force. Okay, so if I have a mechanical advantage of, say, 5, and I apply 100 newtons of force, it will multiply my force by 5 and lift something that's 500 newtons. I can lift heavier things. Number 18, what is a wedge? It's basically 2 inclined planes back to back. So here's an inclined plane. Here's another inclined plane. All right, that's a wedge. That's also like what a knife or an axe look like, or the blades of a scissors. But it can separate things by applying big forces outward as you push it a small distance inward. All right, a joule. A joule is the unit of, I'm just going to write it down over here, unit of work and energy. Efficiency is the percent of work that you get out from a machine compared to work you put in. All right. Efficiency can never be 100% or more. All right. Your efficiencies of any machine will always be less than 100%. So if I have a 50% efficient machine, that means let's say I'm putting in 200 joules of work, the machine will give me 100 joules of work back. But I can't ever get exactly the same amount. And the reason for that is every machine has friction in it. So when I apply a force to a machine, some of my force has to go into overcoming the friction. Well, overcoming that friction doesn't lift the object I'm trying to lift. Then I also have to apply force to lift that object. So some of my work is wasted. So obviously we want to make our machines have as little friction as possible so that they are more efficient. All right, 21, a watt is a unit of power. All right. Okay, once again, if you guys have questions, feel free to stop me, or I'm just going to keep rolling on. Like I said, you can type a note into the chat here. Okay, now number 22, I just actually answered. Can efficiency ever be more than 100%? Why or why not? And the answer again is no. And the reason why is friction. All right, 23, how can you increase potential energy? So if you go and look at the pendulum problem I did before, I said that whenever you're at a maximum height, that's where the potential energy is the most. Well, so then what do? We can increase the height. Right, so for example, if I have a bookshelf, like here's a wall, and I've got 3 bookshelves, I could put a book here, or I could put a book here, or I could put a book here. The higher I go, though, the more and more work I need to do, and the more work that will be stored as potential energy. So greater height means greater potential energy. What are the units of any kind of energy? As I said before, those are joules. Units of work, joules. Kind of repeat questions there. All right, so then we get to this question, what is energy? And that's kind of the big important topic of physics. And so energy is the ability to do work. Right? If I want to lift something up to a higher and higher shelf, I have to have energy in my body to be able to do that. I can't just freely make things happen. I literally have had to eat food that has stored energy from the sun in it. My body has to break down that food into energy I can use, and then that causes my muscles and my brain to work, and then I can do actual things. I need energy if I want to do work. 27, why do work and energy have the same units? Again, it's because they're sort of the same thing. You do work to store energy, or you do work to make things go faster. So work can be done, but you need energy to do it. Whoops, do it. It can be stored as PE, or it can you can do work on an object to make something go faster. You can increase an object's speed, therefore making KE increase. Okay. So, yeah, really work and energy are two sides of the same coin, so to speak. All right. 28, what are the 6 types of simple machines? We have the wheel and axle, and that's one machine, even though it's 2 words. So you've got the wheel and axle. You've got the inclined plane. We did a lab on that. We've got the lever. We've got the pulley. We've got the wedge. We've got the screw. All right, now, the inclined plane, the wedge, and the screw. The wedge and the screw are really just versions of that inclined plane. So those 3 things go together. All right, what's a compound machine? It's 2 or more simple machines working together. All right, so what are some examples of compound machines? A scissors. Even though a scissors is seems simple, a scissors really is at least 2 machines. You've got a lever. Because the screw that holds the 2 blades together, each of the blades is shaped like a wedge, though, and so you actually have wedges and levers working together in a scissors. A bicycle is an example of a compound machine. You've got wheel and axles working together there. Johnny just said, is the scissors a wedge? A scissors is an example of both a lever and a wedge together. Okay, so if I have a scissors, like this, okay, this is my fulcrum. It's actually 2 levers, right? This is 1 lever. This is another lever. And I provide an input force here. And then this is going to provide, whoops, an output force here. There's actually an output force here and an input force here. Okay. Now, these blades here are wedges as well. It's like 2 knives, and they're going to cut the paper. So that's a compound machine. All right, where was I here? Okay, number 30. How does speed affect kinetic energy? More speed gives you more kinetic energy. More speed does not affect potential energy. Okay, so if I'm 50 meters up in the air and I'm just floating, I have a certain amount of potential energy. If I'm 50 meters up in the air and flying in a straight line, I still have the same potential energy. I have more kinetic energy now too, but my potential energy is only affected by mass, gravity, and height, not by speed. All right, number 31, how can you figure out the mechanical advantage of a pulley system by looking at it? You just count the segments. supporting the load. All right, so for example, okay, in this case here, I would have, say, a fixed pulley, right? There's only one segment that's supporting that weight. When I pull down, this rope is not supporting or lifting up the weight. Okay, come on. Refocus here. There we go. Not supporting, but this one is. So this would have a mechanical advantage of 1. Now, let's say I have a movable pulley. Right. Now, in this case, there are 2 segments, 1, 2, both of them providing upward force on the load. This would be an MA equal to 2, whereas this is an MA equals 1 situation. All right, number 32. Why does it seem easier to move something up a ramp than to just lift it up? The reason for it is you don't have to apply as much force. You apply less force. Now, the catch is you have to go over a greater distance. You must push a longer distance. All right, number 33. Why would you want to reduce friction in a machine? That would be to improve its efficiency. Okay. Like I said, when you apply work or apply force to a machine, you want your energy and your work to go into moving the object you want to move. You don't want to just be overcoming friction, because that's a waste of your energy. So if you can make a machine that doesn't have a lot of friction, that's going to be better for you. All right, number 34, do machines decrease the amount of work needed to move an object? The answer is no. Again, you still have to do, at a minimum, the same amount of work. But even then, that's not true. You always have to you actually end up doing more work anytime you use a machine, because you have to overcome the extra friction that the machine brings. However, that's not the same as saying, does it not make it easier? Machines make work easier because you apply less force. That's where you feel the exertion in your body. Now, you're going to, like I said, you're going to have to move it for a longer distance, but that's not hard to do. That doesn't feel hard to do. Okay. So do machines decrease the amount of work? No. They still need, they just trade, I should say, force for distance. And 35, why do people use machines? To either change direction of forces. Okay, maybe like over here on this pulley, I can't lift that up using just the muscles in my legs. But if I grab onto this rope and use all of my body weight and I just kind of sit down, gravity is going to help me. Okay, I pull down to lift up, so I change direction. Sometimes, like in this situation here, if this is 100 newtons, right? Well, each rope is going to support that weight. So this is going to pull up with 50 newtons. This is going to pull up with 50 newtons. All right, so now I'm using less force. So I can change the direction of the force. I can change the amount of force, and I can change the distance. or speed. I can make things go faster. All right, 36, can energy be created or destroyed under normal circumstances? The answer is no. Law of conservation of energy says it cannot. So then the question becomes, if energy can't be destroyed, where does it go? Because let's go back to the example of the pendulum, right? This right here. Okay. If I have a swing going back and forth, I know that if I leave it, it's eventually going to stop. It's going to come to a stop. Well, that violates the law of conservation of energy. But the truth is, there's more to that environment than just the swing. There is friction where the chain meets the crossbar up at the top. There's air resistance pushing back. So some of that energy gets absorbed by the structure that's holding the pendulum. Some of it gets absorbed by the atmosphere. Any sound or heat that is made gets absorbed. So basically, we can blame friction for stealing energy, basically, and it goes into the environment. Anytime you jump up and you land on the ground, you create vibrations. The earth absorbs that energy. 38, how does mass affect kinetic energy? Kinetic energy, if you increase mass, you increase kinetic energy. So if mass goes up, kinetic energy also increases. All right, 39, list the correct units for velocity, mass, power, distance, blah, blah, blah. Okay, so velocity is meters per second. Mass is kilograms. Power is watts. Distance or height is meters. PE or KE is joules. Time is seconds. Force is newtons. Work is also joules. And mechanical advantage has no unit. Mechanical advantage is just a ratio. All right, 40, how are efficiency and mechanical advantage different? Efficiency compares work, and mechanical advantage compares forces. Right? So that's how they're different. How are they the same? You are comparing in both. You are comparing input to output. All right. Finally, 41, name some devices that use electrical energy. You can name about 1 billion different things that use electrical energy. Hair dryer, stove, computer, phone, you know, the list goes on and on. Anything you plug in or charge or use a battery for that uses electrical energy. All right, last page. All right, what do you call a coil of wire that has an electric current running through it and produces a magnetic field? So if I had a battery here, okay, and I had a plus and a minus end, and then I took a wire and I made a coil. Of wire. When I connected that, I would end up with a magnetic field running through that coil. And that coil is called a solenoid or an electromagnet. All right, 43. What device changes mechanical energy to electrical energy? Well, what do we need to do to get electrical energy? We need to generate it, and we generate it with a generator. All right, 44. Why do conductors conduct electricity and why do insulators not? Conductors have free electrons just roaming around on the outside of the metal. And so those free electrons are able to carry energy from one place to another. Insulators do not have free electrons. All right, 45. How do two positive charges interact? How do two negative charges interact? How do opposite charges interact? Basically, like charges or same charges repel. Opposites attract. All right, 46, describe a series circuit and then describe a parallel circuit. Basically, I'm just going to say this. Series circuits are one pathway. And parallel circuits have more than one pathway. All right, 47, when a changing magnetic field inside a loop of wire creates an electric current, the process is called, the answer here is induction. 48, how do the poles of magnets interact? Again, like or same poles attract. I'm sorry, repel. Likes repel, opposites attract. All right, and then finally, number 49, what direction what direction do magnetic field lines go around a magnet? So if I have a magnet that looks like this, north and south pole, magnetic field lines go from north to south. So north to south for that. All right, I think that's all I got.